All right, so very quickly, we're going to get ourselves into section 9.1. We're just going to cover some of the basics. There'll be a little bit more work we'll do with section 9.1 to finish it up after we complete next week the chapter 8 test. In chapter 8, we went through confidence intervals, and now we're going to go through with significance test, or what also maybe would be called hypothesis test. And what are we going to target ourselves for in this little quick unit? Well, in this little unit right now, we're going to go back and work on what are the concepts of these hypotheses in significance tests. And we'll talk about a null and an alternative hypothesis. In confidence intervals, we computed an interval, a lower value and an upper bound. In statistical tests, we're going to do something a little bit different. We're going to compute a probability. We're going to call that a p-value. We're going to look at that p-value and the particular numerical value that it takes on, and determine whether the results of a study happen to be statistically significant. More about that in a bit. And we'll make an appropriate conclusion using a significance level. Is this a truly statistically significant result? And can we do something then about some type of inference claim that is being made? And then we'll wrap up when we go a little bit deeper into this chapter and this section. We'll handle that last checkmark item, type 1 and type 2 errors, in more detail a little bit further down the road, but not in today's lecture. So we're going to start with kind of a basic deal, and we'll go through a couple pieces we talked before. Confidence intervals is one of the common types of statistical inference. We use a confidence interval when our goal is to estimate a population parameter, typically a population proportion or a population mean. Now, the second type, and that's what we're talking about now, significance tests, it has a different goal. We're going to assess the evidence using a probability, a p-value, provided by sample data, and we're going to assess evidence about some type of claim concerning a population, and we're going to use the sample as the means of assessment. And so here's some definitions. A significance test is a formal procedure for comparing observed data with a claim, aka a hypothesis, whose truth we want to assess. We're trying to make inference about a claim. The claim, it's a statement about a parameter, such as p, or the population mean, mu, and focus on what you see in this highlighted section, the color coding. We express the results of a significance test in terms of a probability. And that probability is going to be used as a gauge to measure how well the data and the claim agree with each other. So you express the results of a confidence interval with a lower and upper bound at some type of confidence level. A significance test, we're going to present a probability to measure how well our data from the sample and the claim agree with each other. So let's go through with a little bit of an example. This is something from the textbook. A basketball player claims to make 80% of the free throws that they attempt. That's a claim. I believe that I do this. What's the probability that the player makes no more than 70% of the next 100 free throws taken? Well, you might recall that's nothing more than a binomial CDF type of problem, which I could come back and say, well, the answer to that is binom CDF, 100 trials, 80% chance of success, and I want to have no more than 70 successes out of those 100 shots. And we come back with a probability value that's just a little bit bigger than 0.1. Now, again, to speed things up, I'm going to go ahead and just kind of answer all the questions that you see here since we're working on an asynchronous day, and we'll use our calculators to answer the next couple questions. First, I'd like you to use that sample result above to build a 95% confidence interval for the percentage of free throws made and evaluate the player's claim. Then change to a 98% level and evaluate the claim. Well, if we remember our calculator skills from chapter 8, we could run a one sample z interval proportion confidence interval with x equals 70 and n equals 100. We'll run it at a confidence level of 0.95. And when we calculate, we'd come back with that interval. There's our 95% confidence interval. And you'll notice it does not include the value of what? 0.8. It's not in the interval. It's not one of the plausible values. We would reject the claim that the player is making that they are an 80% free throw shooter. But if we changed and we ran the second piece at a 98% level, you can see what we'd set into the calculator. Here's what would now come back. Our confidence interval needs to be a little bit wider because our confidence level has increased. And now, lo and behold, what do you know? Well, 0.8, it's now one of the plausible values. And you notice I kind of said afterwards, barely. So in one case, a confidence level leads us to reject the player's claim, but another one makes us at least say, hey, I cannot reject it. It's plausible, barely, but there's nothing that allows me to reject it. So just kind of an interesting initial thought here. And we'll talk more about this as we keep rolling forward. Here's the next piece that I want you to think about for a moment. And that is, could both of my answers, rejecting the first time, saying plausible the second time, could both of those assessments that I've made be wrong? And the answer is, to unveil it, absolutely, positively. Pure chance could come into play on both sides with anything like this. There's no guarantee here. And that's the key thing I just want you to be aware of at the moment. What you're seeing here is perfectly correct. It's using exactly what we say to do with confidence intervals. But just remember, this is all pure chance. Chance variability still exists. And it is certainly possible that our evaluations, the way we've looked at the claims with these two different intervals, it's not an ironclad guarantee that we're right. We certainly could be wrong. Mark that, tuck it away. It's a key piece that we need to be aware of as we continue to work through everything that we do with inference. So let's go ahead and look at something a little bit more deeply. And again, it's that same scenario. Here's our basketball player. And this is an example from the book. Basketball players saying they claim that they do make 80% of the free throws. We can run some simulations through this applet you see. When you read chapter 9.1, they're going to give you a slightly different URL, but this is the URL to go to. So you can just kind of paste this and run this at your own. I'm going to go ahead and jump over very quickly and move over to this applet as well. And so I just want you to kind of see what maybe could happen from some of our different samples. And what this applet's going to do is, hey, there's your claim value that you can see, hey, I'm an 80% free throw shooter. And what I'm going to do when I hit the shoot button, I'm just going to take 25 free throws. And you'll see the timer just kind of keeps counting whether I make or miss or whatever. And you can see kind of my percentage of shots made. It'll take a little bit to do 25 of them. I'm going to actually hit the shoot button and do it one more time. And so here comes another 25. And then what under the covers is this simulation actually knows the true probability, the true proportion that this shooter happens to do. And so, here's our example. Well, does it look like this is an 80% free throw shooter? Well, if we hit the show true probability, you'll see that, hey, this is really a 60% free throw shooter. Do you see that they ever got close to 80%? Nope. Does it sure look like they're less than an 80% free throw shooter? The answer is certainly yes. Let me choose a new shooter. I'll hide the probability. Let's just pick a new one. Let's start some shots. Let's see what happens this time. Nope, looks like we got another lousy free throw shooter. Let's just let this thing go up to 25. Unfortunately, it's a little bit slower than I would like it, but that's okay. This sure doesn't look like this is really an 80% free throw shooter. Oh, hey, look at that. It was someone who just can't even make 50% of their free throws. Let's try one more. Hopefully, maybe we'll get this time a better deal. Someone who's a little, whoops, I got to clear out. Here we go. So now let's restart. There we go. So new 25. About the same. Hey, are we getting a little bit better? We're still kind of drifting, but what are we seeing on this go around? Well, at least it looks like you're closer to meeting the claim this go around. Let's go ahead and take a look at what the true value is. Hey, that actually was an 80% free throw shooter. And it turns out that, hey, I got an 80% free throw shooter who happened on these 25 most recent shots only made 68%. Could this have happened? The answer is absolutely. Could this really be the chart of someone who is an 80% free throw shooter? In this case, it absolutely is. So do a little bit of reading from the textbook here. You can fool around with this applet, read it in a little bit more depth. But what it is showing is the power of what we can do with simulation to start testing some of these claims. I'm going to move back over to our slide and we'll see that in a slightly different way. So bear with me one second as we slip back into our activity here. So I'm going to move forward and let's talk about what a significance test is. It starts with a careful statement of the claims that we want to compare. And those claims are going to be hypotheses. The claim that we're going to assess against, weigh evidence against in a statistical text, that's called the null hypothesis. And it'll be written as H sub 0. And often that null hypothesis is just a statement of no difference. You'll see another version that I'll talk about in a second, another definition in a moment. The claim about the population we are trying to find evidence for is the alternative hypothesis, H sub A. H sub 0 is often just kind of, hey, the long-term trend, what I've seen historically. It's kind of the status quo. It's the, hey, let's not rock the boat. This is just the way it's been. And so that's often what your null hypothesis will do. And a lot of times you're going to try to, you'll see this as we do experiments and other things, we're trying to what? Impose some type of treatment, and we hope we're going to see something different than the status quo. And that difference from the status quo is typically expressed as an alternative hypothesis. So in our free throw shooter example, our hypotheses are, well, the status quo is, hey, I'm going to believe this person's claim. They really have been an 80% free throw shooter. The skeptics among us are going to say, you know, I don't really think you are. I think you are somewhere less than an 80% free throw shooter. Notice that the proportion, P, the population proportion, is what we're using here as our random variable. So as we state hypothesis, a couple things. The null hypothesis is always of the form parameter equals value. There always is going to be an equality, and it's always a parameter that you are working with in the null hypothesis. And for that matter, in the alternative hypothesis, which could take on one of three forms. Your parameter is less than the value specified in your null hypothesis. Your parameter is greater than that value. Or simply your parameter is not equal to that. So note, in a null hypothesis, you always have an equality statement. In the alternative hypothesis, you always have a not equality, whether less than, greater than, or not equal to. You always have some type of inequality in your alternative hypothesis. To determine what the correct alternative is, you just got to read the problem carefully. As you read through, you'll see where the bias, where the thought process for the alternative lies, and you'll be able to figure out which of those three color-coded statements you'll work with for your alternative. Now, that alternative hypothesis, if it happens to fit what I have here up top in blue or green, that's called a one-sided alternative hypothesis. It's either expecting us to be larger than or less than the null hypothesis value. And the red version, when I have just not equal to, that's called a two-sided alternative hypothesis. All I care about is that the parameter is different from the null hypothesis value. I don't care whether it's greater, smaller, a lot greater, a little bit smaller, a ton smaller. I just care that it's not the same. And that's what a two-sided alternative hypothesis will track us into. A couple more key things to think about as we do this work. Hypotheses always need to be evaluated, created before we see the data. And that's a good phrase here in the second sentence. It's cheating to look at the data first and then frame hypothesis to fit what the data shows. Hypotheses always are working to a population, not to a sample. So always make sure that your hypotheses are stated in terms of population parameters. You never should see a p hat. You never should see an x bar in your hypothesis. You would be seeing a p and a mu. So just be aware of these key facts. Now, let's come back to some reasoning with significance tests, and let's return to our 80% free throw shooter. Let's do something similar to the simulation that you saw with that little applet. Let's have them attempt 50 free throws and notice that this player makes 32 of them. The sample proportion of made shots is 32 over 50 or 64%. What can we conclude about the claim based on this sample data? And this is where the textbook does a good job, and it mirrors a lot of what we've done before. Remember how we lots of times go ahead and simulate something. So what we will do very quickly to see, well, how unlikely is that 64% result if they're really an 80% shooter? Let's run 400 samples, 400 sets of 50 shots, assuming that the player is really an 80% shooter. And let's see what sample proportion I get each time. And that's what the book will say. And what we can do then after we work through this example, you can see a nice dot plot of the 400 results of the 50 shot sets. We can see how strong the evidence is against the claim by taking the probability, in this case, of what's the likelihood that the player makes as few as 32 out of 50 free throws if he truly is an 80% free throw shooter. And if you look here, what do you notice? Out of all those sets of 50 shots, there's only 3 of them where 64 or less were made. And so what can we say? Well, based on our simulation, our estimate of the probability of making no more than 32 is nothing more than 3 out of 400 or less than 1%. It's 0.75%. Now, how do we assess what we see here against the claim? What you also might notice is you're seeing a p-value right now. We've come up with an estimate of probability under the assumption that the player is an 80% shooter. So let's pull back here. The observed statistic is so unlikely if the actual parameter for p equals 80 gives us convincing evidence that the player's claim is not true. And so there's 2 ways, 2 possible explanations for the fact that this player only made 64% of those 50 free throws. And what could we say they are? Well, number one, hey, they really are an 80% free throw shooter. And it just turns out that they had that ridiculously rare, highly unlikely day when they only made 32 out of 50. Or the other conclusion we come to is that the alternative hypothesis is correct. You know what? This person, doggone it, they are not an 80% free throw shooter. They are certainly below that. Well, maybe not certainly, but I am very, very suspicious. I'm very confident. There's a lot of evidence that would indicate that not only is this person not an 80% shooter, but they are definitely a less than 80% free throw shooter. And that's the way in which we'll go ahead and interpret these pieces. We'll work some more with these. You'll see some examples in a couple seconds as well as we get into our classwork. All right, so what next? Here's your basic idea. An outcome that would rarely happen if the null hypothesis is true, in this case, less than 1%, is good evidence that the null hypothesis is not true. Key thing, it's evidence, not unsubstantiated, ironclad proof, just good evidence. So make yourself aware of that fact as we're walking through. And you're going to see a few more of these basic idea statements as we keep plugging along. So the null hypothesis, H sub 0, states the claim we are seeking evidence against. And the probability that measures the strength of the evidence against that claim is called the p-value. And again, our p-value was what? 0.75% in the scenario that we just talked our way through. So here's a good definition of the p-value. The probability, and notice my highlighting here. First highlighting, the probability is computed assuming that the null hypothesis is true. And that probability that the statistic would take a value, note the next, as extreme as, or more extreme than, or less extreme than, either way you want to look at that second piece, then the one actually observed is called the p-value of the test. We were looking in the free throw shooting example for what? An extreme value 32 or even less than 32. So as extreme as 32 or extreme as being, in this case, even lower down the scale than the one actually observed. And that's what our p-value is all about and what it stands for. What do you know about a p-value? Well, this hopefully isn't a surprise. Small p-values are evidence against. Again, evidence, not proof against H0. Why small p-values are evidence in this way? It's because they're implying that the observed result is unlikely to have occurred when the null hypothesis is true. Large p-values fail to give convincing evidence against H0, fail to give us an ability to reject H0, because these large p-values are implying that the observed result is likely to have occurred by chance when the null hypothesis is true. So that's kind of, again, a new way of phrasing that big picture concept that you saw a couple slides back. Small p-values, evidence against H0. Large p-values fail to give evidence against H0. And so what does this lead us to? Well, it's the final step in significance test, which is the two results that you see kind of on the middle of the screen right now. We're going to draw a conclusion, not a definitive conclusion, but our own interpretive conclusion about the completing claims, the null and the alternative hypothesis being tested. And we're going to make one of two decisions based on the strength of the evidence, AKA based on the p-value. So the strength of the evidence against the null hypothesis, and then just parenthetically, and in favor of the alternative hypothesis. And those two conclusions that we can make are, we're going to reject the null hypothesis or fail to reject the null hypothesis. Please highlight both of these statements: reject, fail to reject. Those are the two statements that you will consistently make whenever you're working a hypothesis test. Note the following: a fail to reject does not mean acceptance. You're not going to accept the null hypothesis. And it all comes back to, remember on the first slide, could we be wrong? Could there be pure chance here no matter how we're assessing this evidence? And the answer is absolutely. So just be careful here. We're never going to fully prove something. We're just assessing evidence and likely outcomes. So just remember, a fail to reject a null in a significance test doesn't mean that the null is true. So just never walk and say, I'm going to accept H0, or use any type of language that you imply that the null hypothesis is, quote, true. Now, here's that big picture one more time, in a nutshell this time. Our conclusion in a significance test will come down to, hey, if I got a p-value that's small, I'm going to say I chose to reject the null hypothesis. I see convincing evidence against the null and in favor of the alternative. If I have a very large p-value that comes back, I'm going to fail to reject the null hypothesis. I don't have convincing evidence to reject it that would provide convincing evidence in favor of the alternative. Now, for what we do in section 9.1, we're just going to be given p-values. But just like there were techniques and methods that we'll use to build confidence intervals, we're going to see the exact same thing in section 9.2 for proportions and 9.3 for means. We're going to have techniques and methods that will allow us to compute these p-values. More on that as we move deeper into chapter 9. Now, one more piece to kind of tie the intro together. There's no rule for how small, what the threshold is for a p-value to be small enough. There is not one set value out there, no rule for how small a p-value needs to be to require us to reject the null. But what we can do is compare the p-value with a fixed value, a fixed p-value that we regard as decisive. And we're going to call that the significance level. It'll be written as alpha, the Greek letter alpha, as you see here. And so if our p-value is smaller than alpha, we will say that the data is or are statistically significant at level alpha. And in that case, what do? Reject the null and conclude that we have convincing evidence in favor of the alternative. So if you think about it, confidence level in chapter 8, significance level in chapter 9. So one more time, when we use a fixed level of significance to draw a conclusion, for instance, one of the most popular alpha values is 5%. If you think about it for a second, one of the most popular confidence levels is 95%. And so just think for a moment, when your p-value is less than your chosen alpha, then that's going to be, quote, small enough. Your probability is smaller than your desired threshold. That's what alpha is. Alpha is your regarded decisive percentage. In that case, when your p-value is smaller than your alpha, you're going to reject your null hypothesis. When your p-value is less than or equal to your alpha, you will fail to reject the null hypothesis. Right? So we kind of have cycled through a lot of the pieces. Let's do two quick examples. In the 2010 census campaign, the US Census Bureau advertised 10 questions, 10 minutes. That's all it takes. On the census form itself, it said specifically, the Census Bureau estimates that for the average household, this form will take about 10 minutes to complete, including the time for reviewing the instruction and answers. Note next, we suspect that the actual time it takes to complete the form may be longer than advertised. State the hypothesis for performing a significance test. And then there's a second example. I'm just going to bring it up on screen, but let's cycle back to example one more time. Well, what do you see? Well, the Census Bureau has given us, hey, here's the status quo. They're saying that the null hypothesis is the mean should be 10 minutes. We suspect, there's your reading in this particular problem, we think it takes longer. Your null hypothesis is going to be a greater than. I think the mean mu should be greater than 10 minutes. That's all there is to it in kind of defining your hypotheses. Here's another example. Mike's a golfer who would like to improve his play. A friend suggests he get new clubs and lets Mike try out his 7-iron from his friend's clubs. Based on his experience with his own 7-iron, Mike knows that he usually hits his old 7-iron 175 yards with a standard deviation of 15 yards. Sigma equals 15 yards. He's hoping that his new club will make his shots with the 7-iron more consistent, aka less variable. So he takes this 7-iron and hits 50 shots with it. State the hypothesis here for performing a significance test. Well, Mike has established, there's your standard quo, and remember, status quo, and remember, he's looking for consistency, variability. He's more interested in his standard deviation as the problem reads. The null hypothesis, H sub 0, is sigma is equal to 15 yards. That's the status quo for Mike and his good old 7-iron. He's hoping for what? Less variability. His alternative hypothesis with the new club is that sigma is going to produce a standard deviation less than 15 yards. I'll be more consistent with this new 7-iron. So I hope that gives you a little bit of a feel for these structures. Let's add one more layer and let's start talking about assessing a statistically significant result and assessing some p-values against a alpha level. A company has developed a new deluxe AAA battery supposed to last longer than its current AAA battery. Now, that being said, these new batteries are more expensive to produce, and so the company would like to be convinced that they really do last longer before they cut over. They might have to implement new machines, new expenses for the techniques that we'll use, so on and so forth. They don't want to commit to this money unless they feel strongly that they will get that better result. So based on their experience with the existing battery, it knows that it lasts for 30 hours of continuous use. The company grabs an SRS of 15 new batteries from this new production method and uses them continuously until they're drained. And in that case, they saw a sample mean lifetime for those 15 newly designed batteries of 33.9 hours. Now, they ran through some methods. You'll see those methods down the road. And they came back with a p-value for their significant test of a little bit over 7%, 7.29%. What conclusion could be made at a significance level of alpha equals 10% what conclusion could be made at a significance level of alpha equals 5%? Well, in the first scenario, 7% is less than 10%. Our p-value falls below our significance level, our alpha level of 10%. We have convincing evidence to reject the null hypothesis. However, if we decide to work at a 5% significance level, what do we now notice? Well, that 7% is greater than 5%. We do not have convincing evidence to reject the null hypothesis. And so we'll see, depending on what we're trying to do in all these different scenarios, there are implications behind the alternative and the null. Sometimes they involve a lot of money. Sometimes maybe they involve health. There's lots of things that they might involve. And what we'll have to do is make a concerted effort to come up with a alpha level, a significance level that we truly are going to feel comfortable with. Not much different than, hey, what type of confidence level are you willing to live with? And so we'll see, alpha equals 0.5 is kind of the typical default go-to value. But in other circumstances, we'll see there will be different values of alpha that we will want to use in our significance test. So at this stage, we've covered what I'd like to cover. We'll talk about this thing called type 1 and type 2 errors, which all comes back to that first statement all the way back at the beginning. Could we be wrong? And the answer is absolutely. We'll talk about those ramifications as we finish up this section at a later point in time. So that covers what I'd like you to do with section 9.1 in terms of exposure. Read up through the chapter until you get to the section that says type 1 and type 2 errors, and then you can stop your reading. And for classwork, here's what I'd like you to do. I'm just going to bypass these slides very quickly and take you right to the end. I'd like you to work the highlighted problems that you see down there, and this will show in Google Classroom. So from exercise 9.1, this won't take you very long, as a matter of fact. Run problems 1 through 13, just the odd ones, and then number 17. It'll be kind of a quick dip, but what you will see through this is you'll have a very good indoctrination and introduction, to what significance tests, what hypothesis tests are all about. The more refined calculations, the underlying techniques, just like chapter 8 worked, we're going to do that same type of thing when we go through section 9.2 and 9.3. So thanks for your time. Enjoy the rest of your async day, and these exercises should not take you very long.